Hey guys, it's Mr. Sheeline here. This is going to be the video notes concerning Unit 5.3 Part 1 notes. This specifically is going to be covering chemical measurements. This is going to be the unit concerning more or less how it is that we, this is going to be where we are figuring out what it is that we are converting. So in the next section, we're going, in 5.3 Part 2 notes, we're going to be getting into converting certain chemical measurements into other chemical measurements, and we'll get into why that is. Here, we're just starting off on how to measure certain things, because then again, like I said, convert those. So we have to understand the masses of different kinds of measurements here. So we have atomic mass, which we've worked before. There's formula mass, and then there is molar mass. Now, molar mass we really haven't worked with. Formula mass, you could probably deduce what that is so far. Atomic mass, 100%. We have worked with atomic mass before. So what is atomic mass? Well, remember, it's more or less the mass of a given element, but it's just to kind of change the definition now. It's the definition here is the mass of an atom relative to a carbon-12 atom. We measure these in AMUs, which remember is atomic mass units, and also I'll even add in here. How to write that? When we look these up, how to say this? More or less what I'm trying to say is here that when we write down these and when we use these for calculations, we're only going to one decimal place. So measured in AMUs and counted to one decimal place. So what does that mean specifically? Like, what am I trying to say here? Well, it's like this. If we look on our on our periodic table and we look up beryllium, beryllium has an atomic mass of 9.012182. Okay, that's a really long number. Down the line, that is a whole lot of things that we have to contend with, where we'll have, it's possible where I could have 5 different answers by the end of just one question that you guys would have in this class. So to minimize that, and so that we all can come up with the same answer, what I want you to do is that I want you to write down, I want you to measure these out to just one decimal place. So beryllium doesn't, for our sake, has 9.0 AMUs, whereas in magnesium, it doesn't have 24.3050, it has 24.3 AMUs, okay? So again, this is to make sure that our answers are consistent so that when I put up keys for you guys and that I'm grading things, I know exactly what your answer should be, and you should fully expect you should have the expectation of what the key should read, okay? So atomic mass, again, we just take that from the periodic table. Formula mass, actually maybe I'll even add that, found in periodic table. Now, and I'll even add this too, must use Mr. Sheeline's, put Mr. S's periodic table. Now, why my periodic table? So if you guys were to look up these numbers on Google, on Wikipedia, on virtually any other website like P-Table, what you'll see is that what we have in the periodic table that we give you, there's going to be some slight differences. And those slight differences may result in wrong answers down the road. So in order to make sure that we have completely consistent answers, they need to be atomic masses that come out of the periodic table that I give you guys. Okay? Super duper 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 important. Okay? Because again, I'm sorry if you got them from P-Table, if you got them from a website, and they may be accredited website, that's fine. But I'm establishing it now. They need to be from my periodic table. And if they're not, they're wrong. Okay? It's not to say that they're because it's incorrect. It's because in order for this to be as streamlined as possible, we need to just have consistent answers here. Okay? So you have to use my periodic table. Okay, Formula mass, what is it? Formula mass is the sum of the masses of all the atoms in the compound. So you can go ahead and read that. It's not too difficult. Okay, take some time to read that, but just to show you what is all basically mentioned up here, all you're doing is you're separating out all of your elements. So for this example with water, H2O, well, we've got 2 atoms of hydrogen, 1 of oxygen. Okay, what's the atomic mass of hydrogen? Easy peasy, it's just 1. 1.0. Oxygen, 16.0. Okay, so 2 times 1 is 2. 16 times 1 is 16.0. And then you just add them together. And so here you would say that water has a formula mass of 18.0 AMUs. Okay, that's what I'm looking for here. So then let's try this with something a little bit more challenging. So we've got here in aluminum sulfate, we have aluminum, sulfur, and oxygen. Looks like because we got the little 2 there are 2 atoms of aluminum. That 3 is going to factor into both sulfur and also oxygen. So there are 3 atoms of sulfur, 12 atoms of oxygen. And then we're just multiplying them against their atomic masses. Aluminum has an atomic mass of 27.0. Sulfur has an atomic mass of 32.1. And then oxygen, like we just saw before, has an atomic mass of 16.0. Okay. 2 times 27, it's 54.0. 3 times 32.1, it's going to be 96.3. And then 12 times 16 is going to give us 192.0. So then we add all those together, and then we're left with 342.3 AMUs for our answer. Bada bing, bada boom, we've got it. Okay. Excuse me. So that right there is easy peasy, what we're going to be using, what we're going to be using in order to convert later on, because in order to actually make measurements within a lab, we have to convert these into different units in order to physically measure them. Because you can imagine, how is it that we're able to actually measure 1 molecule of aluminum sulfate? It's incredibly difficult because of the size. Atoms make up everything, and atoms are so incredibly small, past microscopic level small, that we need to make a conversion from the atomic level up to the physical level, to the size that we can mess with our hands in order to make accurate and precise measurements. Okay, so this is where molar mass comes in. So from experiments, it was determined that if the number of atoms of 2 elements were equal, their masses would always be in the same specific proportion, no matter how many compose the equal amount. So as an example, if the ratio, and this is important that you really try to understand this, okay, because this will confuse you really quick. So if a ratio of hydrogen atoms to oxygen atoms are 1:1, the ratio of the masses is 1:16. If you multiply the number of atoms of both hydrogen and oxygen by 10, you get the ratio of atoms of 10:10. And therefore, a ratio of their masses of 10 to 160, which reduces to the original just 1:16. So it's to say that masses don't change here when you increase the amount of atoms of the particular when you increase the amount of atoms of a particular element. Okay, they stay the same. Well, at least the individual ones stay the same. So another example, the ratio of atoms in a sample of water will always be 2 hydrogen to 1 oxygen, no matter what the size of the sample. Because of this, the ratio of the masses of hydrogen and oxygen atoms will always be 2:16, or 1:8, no matter the size of the sample. Okay. this is just basic math here. It's just basically to say that you, again, in water, always have 2 hydrogen to 1 oxygen. So what we're preparing here is more or less when we get to the point that we are converting molar mass, or sorry, formula and atomic mass into what's called molar mass, and then molar mass into a separate set of units here. So then you have to ask, well, what's a mole? Okay, what does molar mass have to do with anything? Well, it's based upon a measurement, an SI unit, metric system unit of measurement called the mole. So the mole is the number of atoms of of that element equal to the number of atoms in exactly 12 grams of carbon-12. So again, we're using carbon-12 here as the basis of our measurements. And we experimentally calculate it to what's referred to as to Avogadro's number, which is this right here, 6.02 times 10 to the 23rd. So it's to say here, or sorry, a way to simplify the concept of a mole is that 1 mole of a substance, no matter the substance, is equal to 6.02 times 10 to the 23rd particles of that substance, no matter what the substance or its composition is. So it's a similar way in which a gross is equal to 144 something, or you would say a baker's dozen, which a baker's dozen is 13. Every single time, if you say, hey, give me a baker's dozen of that stuff, you're asking for 13 things. So here, when you're saying, give me 1 mole of that thing, what you're saying is, give me 6.02 times 10 to the 23rd particles of that thing. Okay? So it's to say this, that again, no matter the composition, no matter the stuff, that 1 mole of copper has this many, particles. It has this many, in this case, atoms of 6.02 times 10 to the 23rd atoms or 1 mole, sorry, has this many atoms of copper. Whereas in here, 1 mole of CO2, a molecule, has 6.02 times 10 to the 23rd molecules of CO2, okay? So it's just a way for, this is more or less the equivalency, we're getting closer to the equivalency of physically being able to measure things out in a laboratory. We're taking we're taking atomic level things, and we're more or less making these conversion factors. This is nothing more than just more or less a catalyst for a conversion factor, a thing for the conversion factor, in order to take something that's atomic, make it into a measurable thing at the human level, in a human size. Okay, so then what is molar mass? Well, molar mass is in grams, is the mass in grams of 1 mole of a substance. Okay, and we call it the molar mass. It's to say that this substance, so like copper, based upon its atomic mass, which is what we're going to be doing later on, because of its mass, 1 mole of it is going to be this set of grams. So here is where we are getting to the point where we can physically measure things out in actual grams, okay, and do something with them. The unit label, written as a ratio of grams to moles, so it's grams per mole, okay? The molar mass of a substance is numerically equal to the atomic or formula mass for the substance, so it's calculated in exactly the same manner, okay? Oh, come on. So that's to say this here. So the molar mass here, and this is something that I'm going to be asking you a lot about, is the molar mass. Like when we're working on assignments, I'll be like, hey, what's the molar mass of that? And you need to know what it is, and more or less all it is again, like it says here, it is calculated the same way as just the atomic mass or the formula mass. Okay. The only difference is now we're adding the per mole. What we're doing here is that we are now saying that in every 1 mole, this is the atomic mass of, or the amount of grams, we'll say, in 1 mole of this substance. So using water again, we're going to do the same thing like we did with the atomic mass and the formula mass on the other side. So there are 2 atoms of hydrogen. There's 1 of oxygen. This has 1.0 AMUs. Oxygen has 16.0 AMUs. So 2.0 here, 16.0 there. We then add them together, and then we have 18.0 grams per mole. And that is our molar mass. Okay. Now this will start to make more sense once we actually get to converting and we talk more about why it is that we're trying to convert and what we're doing. But again, simply put, we're taking atomic level things that are not possible to measure in a high school science class, and we're making it and we're converting those units to a point to where we actually can measure them with the tools that we do have. Okay, we can measure out 18 grams per mole of water. That is possible. Okay, so that is the set of notes, part 1 notes. So again, this is setting up the foundation of what we're going to be doing later. Mostly the practice that you'll be doing is more or less finding both the molar mass and also the atomic mass in the next couple of worksheets and the next couple of activities. So just keep that in mind. From this point forward, and something if I didn't mention in the other videos, from this point forward, we have to make sure that we are putting down the correct units, and we have to be writing units for every single answer that we're giving. If you do not have the units here, you're not giving me the correct answer. You've got to have the units, and they have to be the correct units. So when I ask you for molar mass, it better have a grams per mole, okay? It's got to. It has to. If it doesn't, that portion of it's wrong, and you'll have points taken away. So keep that in mind as we move forward. So that's the end of the video, guys. If you still have questions, make sure you get a hold of me. If not, I'll see you in the next one.